Okay, so let's continue. So today we will continue what we started last week or earlier this week with modeling of the quadrocopter and figuring out how to do orientation estimation. So we will start with that, and then we will continue on with the mechanics at the end of today's lecture. How do we set up the dynamic equations for the quadrocopter? But we talked about the accelerometer and the gyro that you have in the quadrocopter. And those you would like to use to get an estimate of how the quadrocopter is oriented. So we will now start with trying to do pitch and roll estimation based only on the accelerometer first. Okay, so last time we saw that the specific force that we measure inside the accelerometer, we have a 3-axis accelerometer, so we have X, Y, and Z. So 3 different forces that we measure. And we measure them in the same coordinate system as the quadrocopter is in. And if we compare that to the accelerations that we have in the world frame, so we have accelerations and then we have the gravity force here. So these are the accelerations in the inertial frame or world frame. This is the gravity. And then it's rotated in some way. And then we measure something here. Right? So we can see. So these are the measured specific forces in the body frame. Okay, and the problem with the accelerometer is that what we measure here will depend on both on the gravity and on other accelerations. And we can't really separate them, but when we try to do estimation of the orientation, we would like to only have the gravity vector here, no other acceleration. So to use the accelerometer to measure the orientation will only work if you have no other accelerations in the system. So we will assume that it is at rest when we do this. So what will happen then? So if the inertial measurement unit is at rest, meaning that AI is equal to 0, then basically we have Fbx, Fy, Fz is equal to some rotation matrix from the inertial to the body frame. And then we put here 0, 0, 1. So I had minus the gravity here, but we assume here that we have the accelerometer is negated to give plus 1g, when aligned with Earth's gravitational field. So we assume okay. So just coming back to how we set up the roll, pitch and yaw. So we have the coordinate system here. We have X, and this was the roll axis. It's called phi. This was Y. And we have theta to denote the pitch. And this was the yaw. Like that. Okay, so okay, so the orientation is then defined by the roll, pitch and yaw. And as we discussed last time, we also saw that it matters in which order we do the roll and pitch. So let's say we do roll first and then we do a pitch. So if we go in this direction, so if we do roll 90 degrees, we'll do like that. And then if we do a pitch 90 degrees, it will turn like this, right? But if we do, instead we start by doing the pitch first and then the roll. We'll go like that. So the order is important, and then you have these different Euler angles that you have to worry about. So you have to set up in which order you do the roll, pitch and yaw. But today we need to have coming back to the rotation matrices. So we have the following rotation matrices from inertial to body frame. So we start with the roll. So this is similar to what we saw in the last lecture, it's just that they are now the transpose of what we wrote up last time. Okay, and then we have R, Y, B, A, fed, theta. So we have the pitch here. So C means cosine, and S means sine. Like this. And then we have the yaw rotation matrix as well. Okay, so, and of course then we have three ways to choose the first one, and two ways to choose the next one, and one way then to choose the last one, if we will do a roll, pitch, yaw. So that means that we have 6 possible orderings of roll, pitch, and yaw rotations. Six possible orderings of roll, pitch, yaw. Okay, so, and in the last lecture we decided to use SSY190, that is called the Tate-Bryan Euler angles. So they are popular for aircrafts. So we start with the yaw, and then we do the pitch, and then the roll. Okay. So now we'll try to connect it back to this. Here, right? So, because this one is known, right? That's the gravity field. And this one is what we measure. And then this matrix here contains the roll, pitch, and yaw angles. Right? And what we now would like to do is to solve for the roll, pitch, and yaw, based on that this is known and this is what we measured in the accelerometer. So if we now set up this rotation matrix with the ordering we had last time, and multiplies that by 0, 0, 1. So it's a huge, we can skip these. Because since we will multiply with this vector, we will only keep the last column anyway. So this, we can look up in any book. And then we have so then we have sine of phi, sine of psi. I need more space to write here. Oh. then multiplied by 0, 0, 1. Okay, and here we get cosine psi, sinus phi, cosine phi, sinus psi, sinus theta. And the last element will be cosine theta, cosine phi. Okay, so we see here we have three unknowns, right? So three unknowns, three equations. So it should be possible to solve, you can think. The problem is that we have an additional constraint here. And that is that, you know, the size of the force vector here is 1, it's a gravity vector. Right? That means that the norm of this vector has to be equal to 1 as well. So you only have 2 degrees of freedom. You don't have 3 degrees of freedom here. So note that the norm of f has to be, which is basically fbx in square plus fyb right? So we can't get a larger force here when we have rotated it than what we started with. So this is of course under the assumption that the body is at rest. Okay, so the problem with this is that we have only 2 degrees of freedom. So we can't solve for 3 parameters here. So the system is underdetermined. But we can do something. So we mentioned that there were at least 6 different possibilities to choose the order in which we do the rotations. So if we then change it to that we'll do it in the opposite orders. So instead of having z, y, x, we will have x, y, z. Turns out that the rotation matrix will look a little bit different. Okay, so then the rotation matrix will be R, B, I, X, Y, Z times the same vector as before. So now we will have something that looks like, so minus sinus theta, cosine theta, sinus phi, cosine theta, cosine phi. Times which of course will be okay, so with this rotation matrix, for this equation that we would like to solve here, we only have two unknowns. So we have the pitch and the roll. The yaw disappeared here. So now we have two unknowns, we have two equations. So this we can solve. Or 2 degrees of freedom. This can be uniquely solved. Okay, so then it's just a matter of looking at the equations here to do that. So we start with trying to solve for phi. So phi is the roll angle. So we can see here that and this should then be equal to FBX, FBY, FBZ, right? So if we now take this divided by that, so then we will get FBY divided by FBX. So FBY will be this, cosine theta sinus phi divided by cosine theta cosine phi. Right, so they will disappear, and then we will only get tangents phi left. Okay, so from this we can say that, okay, phi is equal to acus tangens of FYB divided by FBX. And for the same reason as we discussed last time, we typically would like to use the A tang 2 instead. So we have the FYB here, and then we have the FXB here. So we know which quadrant we are in. Yes?
Are you sure you mean FX is the denominator?
Yeah, it should be Z, of course. Y, Z, here. Thanks. Okay, so this is important now, because now we can, just by, this is what we measure from the accelerometer, and now we can get an estimate of this angle here. which is the roll angle, right? Okay, so then we will solve for the pitch. Okay, so we have the pitch here and here, right? And now we, oh sorry, here, here, and here. And we have now solved this one. So we could basically just do some, if we multiply this with sine of phi, so then we will get cosine times sine square of phi, and if we multiply this with cosine of phi, we will get square cosine here, and then we can add these two together, and then the sine square of phi plus cosine of square will be equal to 1, as you know. So okay, so if we add them up now, so fyb sine of phi plus cosine of phi will then be cosine of theta times s square of phi plus cosine square of phi. And this is always equal to 1, right? And I think that's the answer. So we'll see here. So I will come back to that. So here you had an expression for the cosine of theta. So you have fyb sinus phi plus fzb cosine of phi. Right. And if you now take that into account, you can rewrite it as minus fxb and then square root of fyb like that. Okay, so let's continue. I actually got some very good comments here in the break. So, first about this, which was not too complicated to see. So if yb is equal to cosine theta sinus phi, f zb, we see, yeah. So those we get directly from the equation system we had. Like that. So if we now square this equation and that equation and we add them up, so then we will get fyb square plus fzb square. Then we will get cosine square theta times sinus square phi plus cosine square theta plus cosine square phi. So then we can break out cosine theta square And then we will have like that. This will be equal to 1 again. So then we know that cosine of theta is equal to the square root of FYB square plus FZB square. And of course then we get tangents theta is equal to sinus theta divided by cosine of theta. Sinus theta we had from the first equation, that is minus fxb divided by, and now the cosine theta we had from here. So we get the square root of fyb square plus fzb square. And this was exactly what we had here. So now we know that. And then of course we have theta is then equal to a tan 2, and then we have minus fx b, and then we have the other component here. Okay, so that was the first question I got, and I didn't have a good answer to. But I got another very good question about why didn't we just use the first equation and solved it for arc scene instead. But as someone remarked here, if we go back, so we said that initially when we started, we said that FB is equal to RBI AI minus G. But from Newton we have that F is equal to the mass times the acceleration, right? So what we measure here will depend on this, on a constant here. And if we just and if we do like in the way we did here, so we will have a constant here and a constant here, so they will cancel out each other. So this is most likely the reason why you calculate it in this way. So thanks for very good questions actually. So I think we have an answer to them. No. Yep.
Another question. What's the notation on the arcus tangent there with the 2 and the bracket that never?
This? That's a mistake.
Then, I don't know.
But that I covered that last time. But so arcus tangens will give you get back something between minus 90 and plus 90 degrees. So if you take arcus tangens A divided by B, it will be the same as arcus tangens minus A divided by minus B. So you don't know where you are. But with this arctang 2 function, you will keep track of if you have this situation or that situation. It will give you different arguments. So you will get something between minus 180 and plus 180 degrees instead.
Sorry.
Yes?
Why is the cosine on the left? It's not the negative value when you make the root calculation.
Here?
Yeah.
Why is it?
Why is it not the negative value? It's a positive one. Why there is no?
Yeah, so that has, so what will happen here, so this is the pitch angle, right? So you will only get a pitch angle to 90 degrees. You will never get anything like that. So you will, you see? So given this, it will not, if you're here or if you're here, it will not notice. Hmm? Hmm? Good. Okay, there are so many different aspects that shows up in these when you work with real applications. But we will continue on with a complementary filter that we started before the break. All these roll and pitch angles are now computed under the assumption that that the body is at rest, the mu is at rest, right? So we can have tilted it by doing a roll or a pitch, but we keep it still and in this orientation. And that's the next problem we will deal with, because of course in reality they are not at rest. Yes?
Can you go back to the other board?
Yeah.
Can we come from the Fy sinus theta after cosinus theta 2, the square sum of them and the square root?
This.
How that turn to that term?
Yeah. That's a very good question. I was asking myself that, but I didn't have time to, because I was following some notes where I have done it. So I have to come back to that. I will sort it out. And what bothered me now was that there might be a mistake, so that it's not like that. Instead, it's theta that is equal to that. But let me get back to that. I need to check all the steps in the calculations. And then it should not be like that. So that was...
get there, so...
Yeah. It was not completely obvious how to do it. So unfortunately, I was a little bit stressed when I prepared these. And I will look it up. I will send out an email. What is the correct way to do it? Okay. So we continue. So with the complementary filter. So with the complementary filter now, we will try to merge the measurements we get from the accelerometer with the measurement we get from the gyro. So the accelerometer so the estimations we get from the accelerometer are noisy, meaning that they are affected by the body's acceleration as well, right? So, but they are accurate over a long time. So they are correct in average. They are not sensitive to drift in the same way as the gyro is. The gyro is sensitive. So in the gyro we get the angular velocity, right? And to get orientation we need to integrate it once. And then, of course, if there is a bias, we will that will start to add up, and we will get off the correct orientation after some time. So that means that in the long run we can trust the accelerometer, but in the short run we would like to trust the gyro, because the gyro is not sensitive to accelerations as the accelerometer are. But the gyro has the problem that in the long run there will be a integration drift. Right? So we will then do sensor fusion here. So we will trust the accelerometer in the long run and the gyro in the short run. And then to do that we will use this idea of the complementary filter. So the orientation, estimations, from the accelerometer is noisy. But it's accurate over long periods of time. Under the assumption that it doesn't continuously accelerate or something like that. Okay, the gyro, accurate over the short term, but sensitive to drift over time. Okay, so the whole idea. So can we trust the gyro in the short term and the accelerometer in the long term? And one idea then is that we do the filter, the gyro estimations of the angle through a high pass filter, and the accelerometer estimations through a low pass filter. So we will do that, but I think we take the break now, and then we start to do these calculations after the break. Okay, so we will let theta A be the angle estimation from the accelerometer that we calculated in the way we did previously here. Theta G is the angle estimation from the gyro. Okay, so, and that is the integral of the measurements from the gyro. So this is the angular velocity. So you integrate the angular velocity, we will get the angle. Okay. And then we said before the break that we would like to do a low pass filtering on the accelerometer and a high pass filtering of the gyro. So we will introduce a transfer function here, g of s, 1 over alpha s plus 1. So if we look at the amplitude diagram of this for different frequencies, we see for low frequencies this will have the amplitude 1, right? And then, so we look at now at g of j omega. So for low omegas it will have gain 1, and then for higher frequencies what will happen then is that what we have down here will become larger, right? So the total gain will go down. So we'll get something like that, and the low, and the breakpoint here will be 1 over alpha. And the low frequency asymptote and the high frequency asymptote meet. Okay, so basically here, so if we increase alpha, then we will move this point in the left direction, so we will have a lower cutoff frequency in the low pass filter. Okay, and then we get a high pass filter. So 1 minus g of s is 1 minus 1 over alpha s plus 1, which will be alpha s divided by alpha s plus 1. Okay, in the same way, we have omega here, and then we have so for low frequencies we will have a very low gain, and then we'll have it will be 1 for high frequencies, and the breakpoint will once again be 1 over alpha. So this is the high pass filter. Okay. Okay, so now we will let theta be our estimation from the complementary filter. Okay, so we have theta A, the angle estimation from the accelerometer, and we do a low pass filtering of that data, so we send it through g of s, so a low pass filter, and then we have the measurements, the angular velocity from the gyro. We first integrate, and then we get our estimate of the angle by considering only the gyro. Okay, and that we send through the high pass filter. Okay, and now we add them up. and then we get our total estimate. So, and this way it was designed that the low pass filter plus the high pass filter were always equal to 1. So that's where the name comes from, the complementary filter. Okay, so if we write this down in the Laplace domain, we can say that what we have here on the right-hand side is equal to then the transfer function of the low-pass filter times the Laplace transform of the signal from the accelerometer, plus, and then we have the high-pass filter times what we have from the gyro. And this in turn was 1 over s, because it was the integration of the angular velocity. Okay. Okay, so now we have something in the continuous time. So if we would like to get something in discrete time that we can implement, we can discretize this. And there we have different methods, but we can use, for example, Euler backward. So if we write this as this transfer function as the corresponding differential equation, then every derivative in the differential equation we will approximate in this way. So every time derivative will be x of the signal at the current sample minus the value of the signal at one previous sample, and divided by h, the sample period. Okay, and from this, if we use this, we will get so theta k bracket is equal to 1 minus gamma theta A at sample k plus gamma and the estimation, the previous estimated value, plus h, the sampling time, times the angular velocity of the gyro at this sample. Okay, and where gamma here is equal to alpha divided by h plus alpha. So alpha was the cutoff frequency, h was the sampling period. It's always larger than 0, right? So this constant here will always be between 0 and 1. Okay, so this we get from the accelerometer, this we get from the gyro, and this was our old estimate, and this is the new estimate. Right? So this we can just execute over and over again. Okay, and the only parameter we have to choose here is gamma. Okay, and what does this really mean when we change gamma here? So we saw that H was given, right? So sampling periods, we can't change that, but we can change alpha. So if we take a large alpha, so that means that this quotient will be close to 1, right? So gamma is close to 1, results in a low cutoff frequency. You see here we go back to the low pass filter, we increase alpha, we will move the cutoff frequency to the left. Right? And on the other hand, yeah, results in low cutoff frequency. And what will then happen, we will have a more significant contribution from the gyroscope. So gamma is close to 1. It means we will trust the accelerometer very little, but instead we will trust more on the gyro, right? So if we have a lot of noise, we would like to do that. A lot of noise in the accelerometer. And vice versa. So if we have a small alpha, meaning that gamma is close to 0, results in high cutoff frequency, and a more significant contribution from the accelerometer. And of course this is a trade-off, because if you have very low integration drift, then you can trust the gyroscope more, because it's not sensitive to these other forces, right? But there is always a problem with integration drift. So and the larger the problem is, the more you have to trust the accelerometer. And so this is something, so this is part of the first hand-in you will do. So you should implement a complementary filter on the quadrocopter, so you can see the orientation. And you should choose this parameter, gamma. And you will experiment with it and see what makes sense. So you are not only trusting the accelerometer, not only the gyroscope, but that you have really this blend of the accelerometer and gyro data.
Is it a constant, or should it change over time?
So typically you experiment and then you stick to a constant. You decide on a constant that is not changing. But I mean, in principle, it could change over time as well. So, but that's not usually done, I would say.
Can I ask one thing?
Yes.
For the accelerator estimation we have,
yes,
we should do 2 integrations, right, in order to get that value.
No, we do it exactly as we did before, right? So we had the forces, and then we take the arctang 2 on these measurements. So we'll get it directly from there.
Okay. No integration required.
No. So that's a good thing. Avoid integrations completely. Good. You see, can just, if we write this down, this equation. So if we write it down in using recursive notation, so it's quite similar to a Kalman filter. So we can just view it in this way. So the estimation up to time k minus 1 is should be so. Yeah, so it's the same filter, just expressed in a different way that might be familiar to you. Okay. So now we know how to estimate the orientation here. Now we have the last final thing to worry about, and that is what happens with the mechanics of the quad rotor. Okay, so I will try to draw a quad rotor here. Okay, and then we have the 4 rotors here. Okay, and then if we choose we have X here, we have Y here, and then we will have Z pointing downwards, like that. And then we will have the rotors. As we see, so we will have some thrust here. And we will see, so this and this rotor, they rotate in the same direction. And the other two, they rotate in the opposite direction. So that's the whole idea behind the quad rotor. So the forces will even out, so it will not start to rotate by itself. And we see here, so under the assumption now that we have the front, so if the front is in this direction, yeah, we saw that from X, right? So if X is on this arm out here where you have this rotor, we will get the equations that I write down now. You see, first of all, we will have this distance here. So it will be the same for all the rotors, but we will call that d. Okay, so the rotor speed will be denoted by omega I for every rotor. And the thrust is then an upward vector as we have here. Okay, and they depend on each other, so that basically it's the thrust here, lifting force, is proportional to the square of the square speed of the rotors. So I is then 1, 2, 3, 4, right? Okay, and then we have the translational dynamics in the world frame is given by the mass times the acceleration, so b prime, is then we have the gravity pointing downwards, and then we have the rotation matrices, and then we have from the base to the world frame now 0, 0, t. So now this is, so it will lift in the z direction of the quad rotor, right? So now we need to translate that backward to the world frame. So that we do by going through this rotation matrix from body to the world frame. Okay, so and then we have the torque. Applied to each propeller. Is opposed by aerodynamic drag. Which is proportional again to the, with a different constant here. Okay, and now if we look on the generated torque, so run the z-axis, so the torque z is equal to, then we have q, what's from the q1 minus q2 plus q3 minus q4. And since they look like this, we can write this as k, and then we have So of course we can use this now to rotate around to do yaw control, for example. Okay, and then we have tau x. So then we will have in the x direction so rotating around x, we will have d times this thrust we have here, T4, minus d times T2. And then we can rewrite this as like this, and then we have similar to the y-axis. Okay, and then based on this, so we can then calculate the rotational acceleration is given by Euler's equation. So then we have the inertia times the time derivative of the rotational speed is equal to minus omega. And then we have the cross product between the inertia matrix and omega plus big gamma here, where gamma is the vector tau x, tau y, tau z, which is the torque applied to the airframe. So what you will also do in the assignment is to build this model.
Sorry.
Yeah?
What is the difference between the cross product and the omega? The sign is an integral, or is it a j?
This is j. Yeah. So it's the same. This is the inertia matrix here of the frame.
Is it going to be given or don't?
Yes. No. you will get most of the parameters here. Yeah. So but what you will do is that you will write down these equations, and we will use something called SimScape. So SimScape is an add-on to, or you can say the next generation modeling language. So, which is different from how Simulink is built up, because in Simulink you have to decide what is the input, what is the output. In SimScape you can just write down the equations. And you can actually write down equations like that. So we have one line to model this. So of course you need to give the matrices and so, but and then it will figure out what will happen with the frame. So that's quite nice, actually. So we did. So this was basically the equations you needed. But if you're interested in this, you can go to this book that I referred to on the last lecture in robotics. Vision and control. So which is freely available at the library. So if you go to, I think it's chapter 4 there, they go through all this in a little bit more detail. Yes. So we'll see. So after the break, one of the TAs will be here. You, or I think 2 of them will be here. So they will then we will they will show a little bit how to set up this virtual computer and how to do the code generation and to get started with the Crazy Fly. And then if you are already in the group, you will get your quadrocopter as well. And if you're not in a group yet, they will assign you to one group. So I think that